Hi, Tony. How are you?
Good. What about you?
And well, so do you have any questions on the last lecture or any other questions?
Um, Not so far.
Okay. So, based on the last lecture, we have the concept of work, and we said that the work from a point one, the particle, the exerted work on a particle from position one to position two have a general form of the integration from R1 to R2 of the dot product of the force multiplied by the R, and this is equal to S, the integration from S1 to S2 F sine theta ds. So this is the general one, and this is what we know from last time, that if we have a body rested on a surface and there's a force acting on this surface, we will need to find the force in the direction of the motion, because this is the only one that are exerting work, and multiplied by S. And we got the force exerted by the weight, and it's equal to negative. Sometimes it's positive, depends on like as the particle, like as from the example from the last time, if we have a body and we will move this body on a table, so it goes up, but the gravity is going down, so this will be negative multiplied by delta y. But if the body is here and is moving down, so here's the weight and here's the distance, all in the same direction, so this will be positive, and the work exerted by spring is equal to negative 0.5 multiplied by the k of the spring multiplied by S2 minus S2 square minus S1 square. And we proved all of these last time, and also the work done by a force, constant force P, will be equal to the F constant multiplied by cosine theta by the integration of the ds from S1 to S2. And let's solve this example. So for this example, we have a 10 kilogram block rested on a smooth incline, and if the spring is originally stretched at 0.5 meter, determine the total work done by all the forces acting on the block when a horizontal force P of 400 Newton, so this is a constant force, pushes the block up the plane is 2 meters. So this force, we're able to push this block and overcome the spring force and move it a distance 2 meters. So let's write this problem. So here, let's make it the 30 degree. So here's our horizontal plane. And we have a spring like this, and here's our body. And the body was at, so if this is the unstretched length of the spring, because we need to translate this, the spring is originally stretched 0.5 meters. So this is the unstretched length, which means that S equals 0, and the body was at a stretched length of S equal to 0.5 meter. All right, and then it says that we have a force of a horizontal force, this one, which is 400 Newton. We're able to push this block up to get here, and the distance is 2 meters. So started from this, and this will give us 2 meter, that means that the spring was stretched at 2.5 meter. So let's solve the this problem and let's see which forces is exerting work and which is not exerting work. So just be careful, we have a smooth incline. So it says a smooth, that means there is no friction. So the friction is not exerting force. So let's have our free body diagram to know. So can you mute yourself? Yeah, thank you. So here we have our body here, and we have the weight going down, and we have a spring force. We have, let's put the 400 Newton B, and we have a spring force. So let's put the spring force here. So the spring force, this is a horizontal force, but the spring force is in this direction. So here is the F spring. And we have a normal force if we want to put all the forces. So we have a normal force perpendicular to the surface like this. And if there's a friction, and we know that this body is moving this way, so there will be a friction in this direction, but it's a smooth inclined surface. So if a friction is equal to 0. So this is all the forces on the body, the forces that can exert work. So first, we know that there is not a friction. And we know that the normal force is perpendicular to the direction of the motion. So we know this body is either moving this way or moving this way. And it's stated in the problem that the body is moving this way because it makes distance 2 meter. So we know that the normal force is not exerting any work. So what else is exerting work? So the weight is exerting work, but not all the weight. It's a component of the weight is exerting work. Why? So we know that this surface has an angle 30 degree. So we know that this angle will be a 30 degree as well. So the only component of the weight that are exerting force, we will have here W cosine 30, and we will have in this direction W sine 30. So W cosine 30 is something similar to the normal force. It's perpendicular to the motion direction. So it doesn't exert work. So this component of the work doesn't exert work, but this component exert work, this one. And it's exerting negative work because it's in the opposite direction of the motion. So we know that this body is moving in this direction and the weight is going in the other direction. So the weight is putting negative work on the body. And also the spring as well, because the spring is always in the opposite direction of the motion. So the spring is putting negative work, but the force B putting a positive, and not all the B, it's just like a component. So we will have also to analyze B. So you will have this angle is equal to a 30 degree, and you will have the cosine component of the B is exerting the work, and the sine component. So you have B like this, and you will have to get the component. So you know that this is theta. So you will have B cosine theta and B sine theta. So B sine theta is not exerting to the direct, this is the only component that exerting work. So right now we know all the forces. So let's start solve the problem. So okay, so we have, let's get the work done by B. So UB will be the integration of R1 F dot product by dr, and this is S1 S2 F cosine theta ds, and we know that F is constant, so UB will be equal to F which is a 400 cosine 30, and the ds, like, it will be S2 minus S1, because if we talk all of these outside cosine theta, it will be S1, S2 ds, so it will be F cosine theta S2 minus S1. So we know that S2 is equal to 2.5 here, and the S1 is 0.5. Or you know that delta S is equal 2 meter, and you put 2 meter here. And when you calculate this, it will give you 692.82 Newton meter or joule. So whatever the units you would like. So this is the work done by the work done by horizontal force. Work done by horizontal force B. Let's get the second one. Work done by spring. So the U spring, we know, we proved this last time here. It's equal to negative half K multiplied by S2 minus S1. So it will be negative half multiplied by K multiplied by S2 square minus S1 square. So we know the K from this problem, it's given 30 Newton per meter. So this will give us negative half multiplied by 30 multiplied by 2.5 square minus 0.5 square. This will give us negative 90 Newton meter. And the third force is the work done by the weight. You weight. So let's see what we have here. Which one is exerting a force? So yeah, we said that we have W cosine 30 here is not against, this is the only one, and it's a negative. So here's the force will be negative W sine 30, and this will be multiplied by delta S, which is 2. So the W is 10 kilogram, negative 10 multiplied by 9.81 sine 30 multiplied by delta S, which is 2 meter. This will give us negative 98.1 Newton meter. So let's right now, and as I told you, the friction, there is no friction, because if there is a friction, it should be included, and it has a negative work, and the normal force is perpendicular, so it doesn't exert any work. So let's get the total amount, the total work exerted. So the total work will be equal to UB plus U spring plus U weight. So we have UB is 692.82 plus the U spring is 90, and it's negative. So negative 90, and the U weight is negative 98.1, and this should give us 504.72 Newton meter. So this is the total amount of work exerted on this particle. So here's, determine the total work. So this is the only thing that need to be determined. So this is how we can solve this problem. And with this, let's move to the concept of work, the principle of work and energy. Does anybody have any question on the solution of this problem?
Yeah, I have one.
Yeah,
For
go ahead.
for finding the work done by the weight, why didn't we just use the
Because
negative W times delta Y equation from the last time?
yeah, okay. So this actually will only work. Yeah, you can do this actually if you want, but so it's the same thing like W, and the same thing you will need to define like here, if your body is here and came here, so you will need to define the delta Y like this. You will have to find so this is the triangle, and this is 2, and you know that this angle is 30. So you find this delta Y and multiply the W by delta Y. And delta Y, when finally you will get it, it will be equal to 2 sine 30. And this should be, you will have 2 here and you will have 2 sine 30. So what I did here, I put the sine 30 with the W and multiplied by 2. So you can do both are fine. Did you get the idea? That you analyze the weight in the direction of the motion or analyze the displacement in the direction of the weight. So both are fine. So you just have to find the right delta Y from this position to this position. Like you have 2 here and you have 30. So you do some geometry to get delta Y, and you finally it will end up with 2 sine 30 and multiply them by the total amount of W. And you don't have to analyze the W in this. But what I did is that I used the total distance 2 and I get the component of the weight, like it was W sine 30 in the direction of this displacement. But if you understand the concept, both will be the same. Do you have any other question?
That's all I got. Thanks.
Okay, sounds good. So let's move to chapter, I think it's 14. Principle of work and energy. Yeah, this one. Chapter 14.3. The principle of work and energy. So let's see what is the principle of work and energy, and I expect that you guys have some background about this. So if we have a body move on a curve like this and start to move at point 1 and end the movement at point 2, and at any random location on this path, there is a force, a resultant force Fr on this body. And this resultant force is equal to the sum of all the forces on this body. So it gives you any direction like this. And we need to analyze this force, one into tangent to the base, F tangent, and one is perpendicular to the back. So F tangent and F normal. And we know that F normal is not exerting any work because it is normal to the direction of the motion. And the only one that exerting work is the tangent direction. And based on Newtonian kinetics, we know that the sum of F tangent, sum of the forces in the tangent direction equal to MA tangent. And we know that the A tangent is the time derivative of the time rate of a change of the tangent velocity dvt dt, and we know that this will be equal to v dv ds. So this and this are the same thing. So let's plug this here in the A tangent. So this will give us the sum of F tangent will be equal to M multiplied by V multiplied by dV ds. And let's put this here. So the sum of F tangent multiplied by ds will be equal to mv dv. If we integrate the left and right hand side, so the integration here will be from S1 to S2 because we have ds, and here from V1 to V2 because we have dv. The results from this integration will be, we can get the sum outside the integration, and you will have S1, S2. The integration of F tangent ds will be equal to half mv2 square minus half mv1 square, because the integration of this will give you half mv square, and the upper is v1, and the lower is v1, and the upper boundary is v2, and when you substitute in the v, it will give you v2 square minus v1 square. And actually, this will give us a very interesting thing, because we know that the integration of the force over a distance is the work done by the particle from position S1 to S2, and we know that half mv square is the kinetic energy. And actually, this is the relationship that relate the work exerted on a particle by the energy of this particle. So we know that this work is the work from point 1 to 2, and we know that this is V2 is the kinetic energy at position 2, and half mv1 square is the kinetic energy at position 1. So this formula will give us that the work exerted on a particle will be equal to the kinetic energy at the final position minus the kinetic energy at the start position. So for example, like the example, actually, we can take the example from the last one. We have the body here, and it has a spring here, and it came here. So there is some work exerted on this body to move from point 1 to point 2. And this is, we call it U12. And this work actually is equal to the kinetic energy of the particle at this location minus the kinetic energy of the particle at this location, T1 minus T2. So this is how the concept of the work and energy works. So, and actually for the energy, it's kind of not similar to the work, because work could be positive and could be negative, but energy is always positive. It cannot be negative. The body cannot have a negative energy. So, and also it's a scalar quantity. It doesn't have a direct. So let's solve a problem, and how can we apply this concept on real problems? Just like I need you to memorize this equation, because we will use it. And here is the. Does anybody have any question on this concept? I hope that we will. Let's copy this. Okay, let's. Oh my God. So until it loads, let's write this problem here. Let's put it simple. Okay. So for this example, it says that we have a 3,500-pound automobile travels down the 10-degree foot on the brakes until he made a full stop, knowing that the coefficient of kinetic friction between the wheels and the road, the mu k, is 0.5. So right now we have friction, so we will have to consider this. So let's draw a free body diagram to understand what kind of forces that exert work and what are the forces that doesn't exert work. So we have, here is the road, and let's assume that this is the car here. So we have the weight of the car goes down, and we have a friction, and we have a normal force exerted by the surface on the car. So this is all the forces that we have. We don't have a spring force. We don't have a constant force because the motor force will be stopped once you push the brakes, and also it is not given. So once the force is that it's not given, so the motor force of the car will not be included. So this is all included. So this is all the forces that we have. So what of these forces that exerts work? Tony, do you know? Does anybody know?
Yes. Part of the weight and part of the normal force.
So does the normal force exert work?
Oh, wait, no, sorry. I meant like the whole friction would also
Yeah,
do
exactly. So
negative.
the friction, the whole friction force will exert work, and a part of the weight, the component of the weight in the direction of the motion exert work, but the normal is perpendicular to the motion, so it doesn't exert any work. So this actually, so we know that this is 10 degree, and this will be 10 degree, so you will have weight W sine theta, let's make it theta, and you will have a W cosine theta like this. The W cosine theta is not exerting work, but the sine theta is exerting work. You can use the full W and then use delta Y. So whatever it's works for you, I like this one. I get the forces in the direction of the motion and multiply it by the total distance. So let's assume that the car made a full stop here at this location, and it's a given that the car is moving with a speed of 20 feet per second. So we know the speed at this location, and we know the speed at this location because that's a full stop. So V here, which is V1, because this is the start velocity or the initial velocity, is equal to 20 feet per second. And V2 is equal to 0 here because it made a full stop. And we don't know the distance S to make this full stop, and we need to find this distance. So let's see how can we find it. So actually, to find the friction, because we know that the friction is exerting work, so we know that F friction will be to the mu multiplied by the normal force. And to know the normal force, we will have to analyze this free body diagram. So we know from Newtonian kinetics that the sum, so let's make it another one here to be more clear. And here's the body. And here is the weight, W. And here is the normal force. And let's assume that this is X direction and this is Y direction. And we know that the car is moving this way, M, A. But actually, it's not about movement, it's about the direction of the acceleration. Let's assume that the direction of acceleration in this way, but actually you can know what is the direction of the acceleration because you have the car is moving this way, but it's decelerating. That means that the acceleration is going. So here's the direction of the acceleration, but this is the direction of the velocity, because you are braking and you are decreasing your acceleration, so it decelerates. So this is the direction of the acceleration. But let's assume it's in the other direction. And let's do some Newtonian kinetics. Let's get the sum of Fy will be equal to MAy. We know that all the acceleration is in x direction, so Ay is equal to 0. And the sum of Fy you will have is in the y direction, and you will have one of the components, the W, negative W cosine theta, because we have W cosine theta and W sine theta. And all of these will be equal to 0. We don't have any forces in the y direction, but we have F of friction in the x direction when we will have F of friction here, but we don't need it because we are dealing with y direction right now. So right now, N will be equal to W cosine theta, and it's a given that W of the car is 3,500 pound cosine 10, and this will give us the normal force equal to 3,446.8 pounds. So we got the normal force. And I don't need the normal force for the work, but I need it for the friction. So right now I can calculate the friction will be equal to mu k multiplied by n, and mu k is 0.5 multiplied by 3,446.8. And this should give you 1,723.4 pounds. So right now I got the friction, I have the weights, I'm good to go to calculate to use the principle of work. So use the principle of work and energy. How did I know that the best way is to use the work and energy? Because it's a given V at the initial of the motion and the V at the final. So I know the energy half m v1 square and half m v2 square will give me the energy at the start and the end of the motion. And we are given S. So S, that means that if I have the forces, I can calculate the work. So no, I don't mean like we are given S. I mean it's required, and we have the forces. So it's better to use the principle of work and energy. So it's better to use that the work exerted from position 1 to position 2 will be equal to the energy at 2 minus the energy at 1. So let's see what is the U12 equal to. So from 1 to 2, we have the weight. So does anybody know if the weight is exerting like a negative work or a positive work? Like the weight, the W sine theta?
Should be positive work, right?
Exactly, because it's in the direction of the motion. It's opposite to the last one because the weight is going down, the component of the weight is going down and the body goes up. So it should be positive because it goes down. And yeah, so let's calculate. So we will have the work W sine theta, so this is the force, multiplied by S, because this is the distance that the weight will run through, or you get the vertical delta S, which will be equal to S sine theta, and multiply it by the total amount of the weight. So either S multiplied by sine theta and multiplied by all the weight. But what I did, I get all the W sine theta in the direction of S and multiplied by S. So this is the first component. So the second component is the friction, and it's in opposite direction of the motion. And we know that the friction is equal to a 1723, so it will be negative 1723.4. So what is the value that I should multiply the friction by? So we know that U12 will be equal to So let's put it actually, we don't have to put number right now. U12, and this will be F of friction multiplied by S, because we know F of friction is in the opposite direction and it has full force, not a component, because it's parallel to the path, and then we multiply it by S. So the value of this, we have 3,500 pounds multiplied by sine 10 multiplied by the S, which we don't know, minus the F of friction, which is 1723.4 multiplied by S, which is also don't know. And let's substitute in this equation. So it should be all of these U12 should be equal to T2 minus T1. So T2 is equal to half mv2 square. How about if we put the symbols here, half mv2 square minus half mv1 square. And let's substitute here. So half m will be equal to the 3,500 pound divided by 32.2, because we need mass, not weight, multiplied v2 square, and we know that v2 square is where the car will make a full stop and it will be zero velocity, minus half m will be equal 3,500 divided by 32.2 multiplied by v1 square. V1 square is the velocity before you push the brake, which is 20 feet per second, so 20 square. So from this equation, you know everything except S. So you can take S as a common factor, and you finally will be able to calculate S, and it will be 19.5 foot. So this is how you calculate S. Does anybody have any question on this problem? It's just like a basic thing. You will get the friction force by applying Newtonian kinetics in the y direction, and then you will apply in the principle of work and energy because the velocities are given, and then you calculate the work, and then you calculate the energy at position 1 and position 2, and finally you will able to find S. Does anybody have any question? Okay. Does anybody know that if there is any other way to solve this problem based on your previous background from the previous chapter? Here's the problem. What if we continue to use Newtonian kinetics? We got sum of Fy to get the normal force. What if we got the sum of Fx to get Ax, and from Ax, we will be able to get the distance. So let's try this route. So what if we got the sum of forces in the x direction, and it will be equal to Ax. So we know that we assume that Ax is in the negative direction, so we'll put here negative. And let's see what is the forces in the x direction. We have the F of friction, and we have the components of the weight in the negative x direction. So we have only these two forces. So we have F of friction minus W and W sine theta will be equal to negative MAX, because we assumed it in negative x direction, and the F of friction is in the x in the positive x direction, and the W sine theta is in the negative x direction. So you will have to be very careful about the signs of the forces. So we got the F of friction from the previous step, and it was equal to 1723.4 minus W, which is 3500 sine 10, will be equal to negative M, which will be 3500 over 32.2, because you be careful, this is weight and we need mass, multiplied by AX. Then you can get AX, and when you will get it, it will be negative 10.3 feet per second square. That means that the acceleration is in negative direction than the assumed one. So it should be this way. Which is rational because the car is decelerating and the acceleration is negative and not positive. And from this rule, you can actually use the, like, you know, that A is equal to V dV ds, and you will have ADS will be equal VdV, and then you will move forward until you get this V square will be equal to V node square plus 2AX multiplied by S minus S node, and this is the rule from your dynamics equation sheet. And you know that the V final is equal to 0 and V node is 20 plus 2 multiplied by AX, which is negative 10.3, multiplied by S, which we don't know, minus S node, which is 0. And finally, you can get S, and it will also be 19.5 foot. So both should give you the right answer. But actually, I would rather to use the principle of work and energy. Okay, does anybody have any question on this problem? Or in the alternative solution? All right, so I'm just like need to make I'm done with the lecture. I'm just like making a few announcements, you know, that you guys having a quiz on Friday, and the quiz should cover. So let's make the quiz. Three. The quiz 3 will have two problems. One will be on the relative motion from chapter 12. And number 2 will have a force problem from chapter 13. So there will be a problem from chapter 12 and force problem from chapter 13. And in this problem, you will be asked to upload your answer, because there will be a partial credit if you didn't get the right answer. So you will be asked to put a final solution, and you will be asked to put your hand right solution, and the handwrite solution will have 10 points. And you will be asked to draw a free body diagram, and you will get points on the free body diagram if it's right, and also the kinetic diagram if it's right. So you will have to put all of these into your problem so you can get the partial credit for this problem. So I encourage you to do this. The second announcement for the midterm exam. So the midterm exam will be either on Wednesday, not not this one. It should be either Wednesday, July 7th. I know that most of you doesn't give attention to the announcement. And actually, the announcement has a lot of information about the midterm quizzes, homeworks, the deadlines. So please read these announcement. And I'm also trying to also illustrate everything here. So the midterm exam, it's either will be on Wednesday or Monday. This will to be decided. And I might decide it like tomorrow. I will let you know. And Monday, which will be Monday, July 12th. So I will let you know. And the time of the exam, actually all of these things to be decided, but just like if you want to prepare yourself, there's at least from 7 to 10 days on the midterm exam. And the midterm exam should cover chapter 12, 13, 14, and 15. We are almost done with the chapter 14, and over the next 3 lectures, we will be done with the chapter 15. So the midterm exam will be covering these 4 chapters. So just like keep yourself alert to my announcement until I make decision about the midterm time. And actually, that's all. Do you have any other questions? Does
I
anybody
had a
have?
quick one on the last quiz.
Okay.
Problem 8.
The quiz 2?
Yeah.
Okay. I think I have the solution of the quiz. What questions? 8 or?
Yeah, problem 8. Unless it's different for everybody.
Yeah.
Okay. Yeah, so this one, I took the derivative with respect to r. I mean, with respect to theta.
Oh,
But how come we don't use theta dot when we plug in the value?
I didn't understand the question.
So I took the derivative of r, which you basically just get 1.2 theta raised to the third. But
yeah,
how come it isn't theta dot instead of?
okay. I got your point. So you derived r is equal to 0.3 theta to the power 4. And when you differentiate this, you differentiate it as 0.3 multiplied by 4 multiplied by theta cubed without multiplication of theta dot, right?
Oh,
Okay, so this
okay.
will be right
Yeah.
if you are getting, yeah, go ahead.
So then you just plug in the thetas, the 2 theta values, theta dot and theta.
Yeah. So I understand that what I understand from you that when you drive this, you didn't put the theta dot, right?
I just used theta dot inside of, so what you have written there, I used theta dot
Oh,
cubed
oh,
instead of just theta dot. I mean, just theta.
you put it here and you cubed all of them?
Kind of.
Okay, so that's not right. So when you drive, like when you differentiate x cubed, you put 2, like if you will drive it like, let's say that this is y, and when you differentiate dy dt of x cubed, it will be 3 x squared multiplied by the derivative for what is here, all of this. So it will be x dot. So this is how you do the differentiation. It doesn't go inside. So you will just like put it outside and it drives this. If you have like a bracket that has 2 plus 6x to the power 5, and this is to the power 3, all of them. So when you drive this with respect to x, let's do it This is y, and let's get dy dx. So when you do this, you will first put the 3 here, and then you will have 2 plus 6 x to the power 5, and you will reduce this to be square, multiplied by the derivative of what is in between the parentheses. So the derivative of 2 is 0, and the derivative of this will be 6 multiplied by 5 multiplied by x to the power 4. So you put it outside. And this is what happened here, is that we first we put the dr dt will be equal to 0.3 multiplied by 4 multiplied to theta cubed, and you will get the derivation of just the theta outside. So all of this multiplied by the derivative of the theta with respect to t, and this will give you theta dot, because we are getting the derivation with respect to time. If it's 2 d theta, so this will be d theta, and this will be 1, so we don't have to put it outside. Did you get the idea? Or
Yeah,
still?
so in the problem with y, you're going to need to multiply by x dot at the very end.
Yeah, by the theta dot. Did you watch the video that has a solution?
No, I didn't know there was one.
Actually, I posted in the announcement from yesterday.
Oh, okay.
And
I missed
actually,
that then.
yeah, if you check the Canvas page here, the modules, so you will find the solution of each quiz. Like you will go to Fridays, you will find quiz 1 and quiz 1 solution. And each Friday you will have like quiz 2 and quiz 2 solutions. So in the announcement, I put everything, like you will just go to this video and you will find the solutions of all the problems.
Okay, that's helpful. Thank you.
All right, that sounds good.
Have a good one.
Yeah, you too. Bye.